In this video, we're going to start talking about the idea of mechanical loading, which is essentially how do materials respond when you start pulling on them or pushing on them. And to motivate this, I wanted to start with this image here, which maybe you can tell what this is, maybe not. This is an MRI as you hopefully know now, in the sagittal plane. We're looking at the ankle joint. So the ankle joint is here, and then the tibia is here. The foot kind of goes off like this. But what I want to point out is not the bones, but the tendon. This black area right here, you can see is the Achilles tendon. And you'll notice it has this big bulge in the middle. And the reason it has this big bulge in the middle is because this is an MRI from somebody with Achilles tendinopathy. Oops. Meaning they have, well, it looks like swelling, but really it is damage to the collagen fibers of the tendon itself. And you'll understand what that means later on in this unit. But how this damage happens is a function of the loads that get applied to the Achilles tendon over and over and over. So if we draw a simplified maybe diagram of how all of this happened, you've got your tibia over here, and maybe we'll draw a simplified foot. The Achilles tendon is like a little rope, or a rubber band, a really thick rubber band, and it's attached to a muscle. It's actually attached to 3 muscles, both heads of the gastroc and the soleus. But what those muscles do is they create a force. So they pull on the Achilles tendon. They stretch it like a rubber band. So that might lead us to think about, well, what happens to a structure such as a tendon when you pull on it? So I'm going to introduce two kinds of graphs here. So let's suppose we went and got, say, a cadaver tendon. We sliced out the Achilles and put it in a little machine. And maybe we would do it like this. We would get the tendon. We would affix it to something solid, and then on the other end of the tendon, maybe we would put a little force measuring device. If you've ever gone fishing and had the hook attached to the spring with the gauge that tells you how heavy your fish is, that is essentially a force gauge, and you can use it to measure how hard are you pulling on something. So maybe if we were to zoom in and maybe with like a little marker or something, we could put some little evenly spaced marks on the tendon, because under the assumption that it's going to stretch out, right, as we pull on it. What we could do is we could make a graph, and the graph that I'm going to make is change in length. So let's write change. I'll write it out for now. In length of the tendon. And so 0 would be just its initial like unstretched length. And then as we pull on it, it's going to stretch out, right? Like a rubber band. I'm going to plot that change as a function of the force. So how hard are we pulling on it? And what happens is something like this. Force is going to go if you've done this with a rubber band, you know what happens. So there's this little interesting business over here that we'll talk about in a future video. But as you pull on this Achilles tendon, the harder you pull, the more it will change its length. And there's an interesting concept here. The slope of this line, meaning the change in the force per unit change in length. If you were an equations person, you could write it out as like delta F over delta L, maybe L for length. That would be the stiffness. That's like how stiff the tendon is. And you would find that if you got maybe a different tendon that was not so big and not so thick, so maybe another good example would be, or a good example for this would be something called the peroneal tendon. I think some people pronounce it peroneal. It is on the lateral side of the foot, and it kind of comes up like this and goes like there. It is and you know this terminology now, it is an everter of the foot. If you do the same thing with the peroneal tendon, which is smaller and not so stiff, maybe it looks like that. So that slope is not as steep, and so as a function of applying force, it does not change its length very much. In contrast, something really stiff, like maybe a bone, would do like, that. Bones do actually change length if you push on them really hard, but it's not very much. They're very, very, very stiff. So this is a really interesting and really useful way to look at the stiffness of a piece of biological tissue. But there's one problem with it, and the problem is that suppose your Achilles tendon is bigger and thicker than mine, but it's like made of the same stuff. That tendon is probably, so maybe this is your Achilles tendon, sort of cross-sectional area. This is my Achilles tendon, cross-sectional area. Your Achilles tendon is probably going to be much stiffer than mine, even if it's made of the same thing. So there's an interesting way to sort of normalize by those differences in area, and that's what I'm going to talk about in the next video.